Hello and welcome to this video where I'm going to talk about how we may solve nonlinear programmings that only have one variable. So let's start. So formally, NLP with one variable looks like this. We want to maximize a function or minimize a function of x, and only x is the only variable here. And the constraint is x must be in a interval from a to b. If a equals minus infinity, then it is the same by saying that x must be less than or equal to b. If b is plus infinity, then it is the same by saying that x must be greater than or equal to a. If a equals minus infinity or b equals plus infinity, it may be the case that the NLP have no optimal solution. So for example, we take a look at this figure here. We can see that we want to minimize this function that looks like this. And the constraint for x is greater than or equals to a up to plus infinity. We can see that if we want to minimize this function, as we go further to the x positive side, x is becoming greater and greater and greater, the value of fx becomes smaller, and it keeps getting smaller. Since we do not have the upper bound for x, it means that this NLP has no optimal solution. Or we can say that this problem is unbounded. Similarly, we can see that if we have this kind of function and we want to maximize the value of this function, and the range for x is between minus infinity up to here, this b point. Same as before, we can see as we go farther and farther to the negative side of x, the value of fx becomes greater. So there is no optimal solution, because if we keep decreasing the value of x, the value of fx becomes greater. Now here is how we are going to find the optimal solution for a NLP with one variable. We need to find all local maxima or local minima. And these local minima or local maxima, they are called the extremum candidates. They are called candidates because finally we will have to check which one among the candidates that has the best, either the largest or the smallest value of fx, and that point is the optimal solution. Back to the candidates, how we are going to find these candidates. We are going to check three cases. Case one is we are going to check the stationary point, which means the point where the first derivation of the function equals 0. And then case two, we're going to check the points where the derivation of fx, the first derivation, does not exist. And the third case is we're going to check the endpoints of the interval a, b. So we're going to check a, we're going to check b. So by checking these three cases, we're going to obtain the candidates, and finally we check among all those candidates which one gives the best value. Best means largest for maximization, means smallest for minimization. So the first case we are checking where the first derivative of fx equals 0. You may ask why we want to check that. Well, let's see examples if not 0. So let's see if the point in which the first derivative of x is not 0. So let's see the example on the left. Let's say our point is x0. We take the derivative at this point, and we can see that derivative here is positive, because you can see that the slope is increasing. So at that point, the derivative is positive. Because the slope is increasing, it means that just before this point, there is something lower than that. And just after that point, there is something greater than that, right? Because increasing means that before that point there is something lower, and after that point there is something higher, which means that this point x0 cannot be a local maximum. Because remember, local maximum means that that point compared to its neighbor, which is the neighbors are relatively close to that point, then that point is the best. Here, that is not the case. Similarly, if we have the another example here, our point is still x0, and then we check the gradient at that point, we can see that here the slope is decreasing. Decreasing means that before that, there is a point that is better than that, and then after this, there is a point worse than that. Which means that again, this point cannot be a local minimum or local maximum because there is something higher than that and there is something lower than that just after that point. So it cannot be a local extremum. Okay, so we can see that if the gradient at a particular point does not equal to 0, then that point cannot be a local extremum. Now let's see the point where the first derivative of the function equals 0. So here we have this point x0, and then the first derivative at this point is 0, which means that it is not increasing, it is not decreasing either. So it's flat. And then you can see that before x0, here the value x smaller than x0, the slope is increasing. And for the point after x0, you can see here and there, the slope is decreasing. So increasing, flat, and then decreasing, it means that the place where the point is experiencing a flat slope, it is a local extremum. In this case, it is a local maximum. In the second example, this is a local minimum because you can see that the first derivative at x0 is 0. It is a flat slope over there. And you can see before x0, the slope is decreasing. And after x0, the slope is increasing. So decrease, flat, and then increase. We can say that, okay, this must be a local minimum. However, there are points where even if the first derivative at that point equals 0, it is not a local extremum. For example, we can see here at this point, the first derivative is 0. But we do not see that point being a local maximum. It is not a local minimum either. So sometimes it is not enough just to check the first derivative. What we're going to do is we're going to check the second derivative of the function. So if we have a point and then the first derivative at that point equals 0, we then check the second derivative at that point. If the second derivative at that point is non-zero, then we may determine that the point is either a local maximum or a local minimum. If the second derivative is negative, it means that our point is a local maximum. That looks like this. Okay, the second derivative negative means that the slope keeps decreasing. Here the slope comes from very positive, positive, 0, and then here decreasing, negative, negative, and then very negative. So that's why we can be sure that this point where the first derivative equals 0 and the second derivative is less than 0, this is a local maximum. However, for the second example, again, this should be local minimum. We check a point and then we obtain the first derivative equals 0. And then we check the second derivative. Here it is positive because the slope keeps getting more and more positive. Here the slope is very negative, negative, flat or zero becomes positive, and super positive here. So it means the second derivative is greater than zero, which means that at the point where it is flat, we can be sure that it is a local minimum. So what if at one point the first derivative equals zero and then the second derivative also equals zero? We can use the first point from theorem 5. So first it says if the first derivative equals zero, and then we check the first non-vanishing or non-zero derivative at that point. So we check the first non-zero derivative. If the first non-zero derivative happens at an odd order derivative, like the third order derivative, the fifth order derivative, and so on, it means that the point is not a local maximum or a local minimum. Okay, so we check the first derivative at that point. We check the second derivative. If it is still zero, then we use this theorem. Check the third. If it's still zero, check the fourth, and so on until we first find the first non-vanishing derivative, and then check whether it is an odd order derivative. If it is, then it is not a local maximum, it is not a local minimum. And then for the other cases, we use the other 2 points from theorem 5. So if the first non-vanishing derivative is positive, so if the first derivative is positive and it happens in even order derivative, like the second order, the fourth, and so on, then it is a local minimum, which we have discussed actually in the previous slide. And then if the first non-vanishing derivative is negative, it happens in an even order derivative, like the second, the fourth, and so on, then x0 is a local maximum, which also has been discussed in the previous slide. So this is how we are going to check using the first order derivative, second order, and if we need to, we are going to do the third and so on to check whether it is a local maximum, local minimum, or neither of them. So previously from the first case, we have collected the stationary point, which is a local maximum or local minimum. Okay, and if those points are local extremum, then we collect them as the extremum candidates. Now we are going to case 2, where we may collect more extremum candidates if exist. So here we are going to check the points where the first derivative of the function does not exist. If at a point the first derivative does not exist, then that point may be a local maximum, local minimum, or neither of them. If they are local maximum or local minimum, same as before, we are going to keep them as the extremum candidates. Here we can see that these 2 examples shows where for a function at a point x0, the first derivative does not exist, but this point is not a local extremum, right? Because here you can see that if we're going to do maximization, just after this point, there's something better than that. In here in the example on the right, same if we are going to do maximization and our point is x0, we can see that just before that point, we have another point that gives the better function value. So these are not local extremum. However, if a function looks like this, then we collect them as the extremum candidates, because here at x0, you can see that it is a local maximum. It is better than the other points in its neighborhood, and the neighborhood is very close to that point. Here we can collect this point as a local minimum because it is better than the points very close to it. Finally, we may check the endpoints of A and B, the interval of X. Let's see, we have 4 cases here. If, for example, for the point A, if the first derivative is positive, means that the slope is increasing. It means that A is a candidate for is a local minimum, so it becomes an extremum candidate that we collect. Okay, because the slope is increasing, it means that that point is the minimum for the local, which means that it must be lower than the other points in its neighborhood. Remember that the neighborhood is defined as very close point to that one. And here, however, if the gradient is negative, means that the slope is decreasing. It means that this point must be a local maximum. Similarly, for point B, here if the gradient or the first derivative is positive, it means that it is a local maximum. And then here, because the slope is negative, it is a local minimum, which means that compared to its neighbors, which is very close to B, this B is the minimum point. What if we check that the first derivative of A or B equals 0? Then we may draw a sketch to see whether it is a local maximum, local minimum, or neither of them. Now we see an example here where it says a monopolist produce a product and it costs $5 per unit. And then if he produces X units of the product, it can be sold for 10 minus X dollars, where X is between 0 and 10, including 0, including 10. And this monopolist would like to maximize the profit. So the decision variable X is the number of the units that this person produces, and then the profit means that how much he sells his product. So the price is 10 minus X, and then this person produces or sells X unit, and then minus the cost, minus the cost, which is 5X. So this is the function of the objective, which this person wants to maximize. So here we have the objective maximize Px, which is just 5x minus x squared, subject to x between 0 and 10, including 0, including 10. So we here have a nonlinear programming with one variable. We are going to apply those three cases to find the maximum point or the optimal solution for this problem. So we have a function up here that we want to maximize 5x minus x squared, and the constraint for x is between 0 and 10. The first case says that we need to check the stationary points. Stationary point means that the first derivative of this function equals 0. So take the first derivative of this, it becomes 5 minus 2x. And then find the point where this first derivative equals 0. And we can confirm that at the points of 2.5, this function equals 0. And then we check the second derivative. So from here, you take the derivative again with respect to x, and then we obtain the second derivative is minus 2. So at that stationary point, x equal 2.5, we can see that the first derivative equals 0, the second derivative is negative, means the slope keeps decreasing. We can say that that point is a local maximum. Okay, so x equal 2.5 is a local maximum candidate, I would say, and then it generates the profit of 6.25. So you obtain 6.25 by substituting this x equals 2.5 to the function px. Okay. And then for the second case, because this function is continuous for all x in this range, the derivative exists, the first derivative exists for all value of x between 0 and 10 for this function, so we do not have any candidate from case 2. In case 3, we are going to check the lower bound and upper bound of the boundaries of x, and then for x equal to 0, we check that the first derivative value of that point is positive. Positive, it means that it is a local minimum. It is a candidate for local minimum. And then for b, the first derivative at that point at x equal 10 equals minus 15, because it is decreasing, means again it is a candidate for a local minimum. So from 3 cases, case 2 generates nothing, case 3 generates local minimum, which we do not need. So the only answer in this case, the only optimal solution is this point, which is local maximum, which happens at x equals 2.5. Now here's an example where we want to maximize a function of fx, but fx is defined differently. From 0 to 3, fx is defined like this, and then from 3 to 6, fx is defined differently. And then what we're going to do is we're going to maximize fx subject to x between 0 and 6, including 0, including 6. Same as before, because we only have one variable here, which is x, then we are going to use those 3 cases to determine which point is the optimal solution. And again, same as before, from each case, we are going to collect the local maximum that becomes the candidate for the optimal solution in the final step. Okay, so let's apply those 3 cases. Now we're going to check the case 1 for that problem. We have 2 functions here, fx. So for each of this fx function, we're going to find the stationary points. Let's talk about the first function first. We take the first derivative of this function, and here's the result, minus 2 times x minus 1. Stationary point means that we find for at which point this first derivative equals 0. So minus 2 times x minus 1, it will become 0 at x equal 1. Okay? So x equals 1 is our first extreme candidates. And then if we want to know whether it's a maximum or minimum point, we take the second derivative of the function. So the second derivative equals minus 2 because the second derivative is negative, means that right after passing this point, the slope will be decreasing. So it means that that point is a local maximum because after that, it will decrease. Okay, so x equals 1 is a local maximum. Now for the second function here, same as before, to find the stationary point, first we take the first derivative of this function. So the result is this, 2 times x minus 4. And then we check where this first derivative equals 0. It happens at x equals 4. To check whether it is a local maximum, minimum, or not any of them, we take the second derivative. The second derivative equals positive 2, which means that right after passing this point, the slope will increase, which means that at that point, x equals 4, it is a local minimum because after passing 4, the gradient will increase. Okay, so x equals 4 is a local minimum. So now we have a candidate, x equals 1 is a local maximum, x equals 4 is a local minimum. And then for the case 2, we check where the function discontinues. We can see that this function discontinues at x equals 3 because right before 3 we have this function, and then after 3 we have that function, the second function. If we check the gradients, then for x slightly less than 3, the gradient is -4. So decreasing with the slope of -4. But for the point 3, slightly bigger than 3, the gradient is -2. It's still decreasing, but it becomes less steep than before. Okay, so x discontinues at x equal 3. But then, okay, we know that um, this function discontinues at x equal 3. Then we need to check whether it is a local extremum or not. Now, this is how to check it. We can see from the figure actually that it is not a local maximum. It is not a local minimum either. You can also check, for example, the point pretty close to 3. At the point of 2.9, the function value is -161. At 3 itself, the value is -2. And then at 3.1, the function value is -2.19. So either before that or after that, there is always a point that is better than that. Better means either it is greater or it is smaller. So this point, x equals to 3, cannot be any local extremum. It is not a local minimum. It is not a local maximum. Now, finally, we're going to check the case 3, where we are going to check the endpoints of the allowable values of x. So we're going to check 0 and we're going to check 6. What we're going to check is first we take the first derivative of the function. So for that function, here's the first derivative. And then we plug in 0 to that function. So we know that at the point 0, the first derivative equals +2. -2 times 0 minus 1 is +2. Because the first derivative is positive, it means that at that point, x0 is a local minimum. And then for x equals 6, we use this function. Take the first derivative, plug in 6 to this function. 2 times 6 minus 4. 6 minus 4 is 2 times 2 equals 4. So it is positive. So this endpoint x equals 6 is a local maximum. Now, because the case is maximization, so we just need to collect the local maximum. So here we have x equals 1 is a local maximum. And then from case 2, we do not have anything. From case 3, we have x equals 6 is a local maximum. So we have the local maxima x equals 1 and x minus 6. Now we compare which one provides the higher function value. So plug in x equals 1 to this function, and then plug in x equals 6 to this function. And then compare the value. It shows that the function value for x equals 1 is higher than the function value of x equals to 6, which means that the global optimal solution for this case occurs at x equals 1. So that concludes the video where we are using these 3 cases to solve nonlinear programming with one variable. Case 1, we check the stationary points. Case 2, we check where the function discontinues. And then case 3, we check the endpoints. And then we collect all the candidates and then finally compare which points gives the best objective function value. And that would be the optimal solution if it exists. Okay, so thank you for watching this video.